My name is Marshall Lisenby, and this is Physics 2212, Lab 6, our final lab, Magnetic Molasses. The purpose of this lab is to analyze magnetic induction, flux, and force through observing data of a bar magnet falling through an aluminum tube and comparing it with computational models. The materials for this lab were a bar magnet and aluminum tube, which were the system, and a glow script, which is our computational model. Also, in this lab, the surroundings is just everything else in the universe. The main results for this lab was that it took experimentally an average of 2.203 seconds to fall through, while computationally it took 2.047 seconds to fall through. Now, for the fundamental principles. First, we have Faraday's law, which says a changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux with induced voltage opposing the change, which is shown in this equation below. The second one is Biot-Savart law, which is a steady current produces a distance-dependent magnetic field around it, illustrated in general with this law below it. And then finally, Newton's laws. The second law, which says net external force equals change momentum over time, or F equals ma. And the third law, which says for every action, there is an equal and opposite reaction, which are integral to this lab. For the procedure, you first find the north and south pole of the bar magnet utilizing the magnometer map from Lab 3 on your phone. And then you drop the magnet through the tube in the same direction every time. And as you drop it through the tube, you'll observe that the falling speed is slowed by the magnetic force from the aluminum tube around it, caused by the induced current from the falling magnet. Now you repeat this step 4 more times, recording how long it takes to fall from the top to the bottom of the tube, and you record all of those data. And to do this experiment, to make a few assumptions. First, that there is negligible air resistance. Second, that the bar magnet acts as a magnetic dipole. And third, that the only forces on the system are magnetic and gravity, and there's no things like friction or collisions getting involved. Now, here is the data I collected through this experiment with the initial conditions on the right, and then each trial of the experiment in the middle, with an average time of about 2.103 seconds to fall from the top to the bottom of the tube. Now, for the computational model. First, we started with our initial conditions, entering the data that we collected about our experiment on the left-hand side you can see here. And then we went and created 2 functions, one to figure out and calculate the magnetic dipole moment of the magnet, and as well as the change in flux as it falls through the tube. For the main substance of the code, we have these models of forces, the 2 main forces being the magnetic force and the gravitational force, which we modeled in our code. And we found the net force by finding the difference between these two, where the magnetic force was resisting the gravitational force. And through this, we could update the velocity and the position of the magnet at any given time, allowing us to create the model. For the visual model from the code, we have first, on the left, the image which is animated in the model that shows the magnet and the dipole as it moves through the tube. And secondly, we have this more important graph on the right, which demonstrates that at first, the gravitational force is more weighted than the magnetic force. It was pulling the magnet down and causing it to accelerate. However, in the middle, when it's in the tube, the gravitational force and the magnetic force are equal, causing it to move at a steady, constant speed. Now, to interpret the simulation, we have a few questions. First, what color corresponds to currents? Well, through using Lenz's law, red is counterclockwise and blue is clockwise. Second, what happens if you flip the magnet? Well, the magnet would fall as before, but the current directions would be flipped due to that law. And then thirdly, how does real-world change in time compare to the computation? Well, the computation was slightly shorter due to some effects of human errors in air resistance and friction. And finally, what does the plot shape tell us about the forces acting on the magnet? Well, gravitational force is greater than magnetic force initially when entering and exiting the tube, but equal to when in the middle of the meat of the tube. For some potential errors within the lab report, we have first that there could have been inaccurate timing and dropping due to human error when recording the actual times for each trial in the experiment, which could accumulate essentially over multiple trials. 2, we have that friction from magnet hitting the sides of the tube, slowing it down. Being that the tube was rough due to the aluminum foil and hard to drop it perfectly vertically through, so some collisions in contact could have reduced or increased that time as a result. And finally, that air resistance could have affected the forces, because that's a third force that would have been acting on the magnet as it fell through the tube because it was not in a vacuum. Finally, to end this lab, we have some important discussion questions. First, what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, from Ohm's law, it says V equals IR. Decreasing the resistance would increase the current induced, causing a stronger opposing magnetic field and slowing the magnet even further. And second, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, overall, there would be less current rings within the tube and would overall create a weaker opposing magnetic field, causing the magnet to fall faster as there's less space and less magnetic charge creating a magnetic force that reduces the falling of the magnet through the tube. And now that is all for Physics 2 lab reports from me. Thank you for watching, and I hope you have a great day.